So as we start thinking about lines in space, it's worthwhile to go back and think about what we know about lines from our algebra experience. So when I think about the question, what information is necessary to uniquely determine a line, there are about three options that come to mind. One is if I had 2 points on the line, I could certainly draw the line. I could also use that information to write the equation of a line. The same is true if I knew 1 point and the slope of the line, or if I even knew the y-intercept and the slope of the line. Notice that those last two are essentially the same, the only distinction between the two being which point I actually know. So now let's go ahead and talk about a line in space. So when we talk about a line in space, essentially the same information is needed. I certainly could write the equations of a line using 2 points. That aspect has not changed. Or I could use 1 point and a direction vector. Now, the reason we have to use a direction vector and we don't use slope is because slope is change in y over change in x, and when we're working in space, we actually have 3 coordinate directions that we have to coordinate. So taking a ratio or making a fraction doesn't make sense with 3 different coordinate directions. So our direction vector that we use to specify the direction of the line has a change in x component, a change in y component, and a change in z component. And these dictate how each of those coordinates change with the variable t or time. Now, just so you know, I prefer to write and think about my direction vector this way because it makes connections to what is actually happening with the line. You will find that a lot of textbooks and others will just call this A, this B, and this C. And just calling those A, B, and C, it doesn't help me connect what's going on in the direction vector. So as I talk about lines and working with lines, I will be referring to these as change in x, change in y, and change in z. So once I have this information about a line, I can go about writing equations of line. Since you're already familiar from algebra with equations of the line in the Cartesian plane, we're going to start there. And what we talk about is easily extended to space. So when we write equations of line, there are actually 3 different ways to write them, but for now we're going to focus on the parametric form and the symmetric form. And over here on the right, we have parametric form, where the equation for x is x naught plus delta xt, where x naught, y naught is a known point. Oh, I can't spell, known point. And d vector equal to change in x, change in y is direction. Okay, so let's go ahead and look at this equation of this line I have here, y equals 3x minus 2. So we know that we need a point, and because we're familiar with slope-intercept form, we know that 0, -2 is a point on that line. Also, we know that slope of that line is equal to 3. But I need a direction vector, so I'm going to think of this as 3 over 1, or we could think about it as any fraction equivalent to 3. And when I do that, we know that slope is change in y over change in x. So I can turn that into a direction vector where my change in x is 1 and my change in y is 3. Now that's sufficient information for me to go ahead and write the parametric equations for this line. So the equation for my x coordinate is my known x value plus, my known x value is 0 plus my change in x, which is 1, t, and my y equation is my known y value, that's -2, plus my change in y, which is 3, t. So that's the parametric form of the line. That line y equals 3x minus 2. Let's go ahead and plot a couple points along this line using our parametric form. Okay, so for example, what if t equals -2? If t equals -2, then x equals 0 plus 1 times -2, so that would be -2. Y coordinate would equal -2 plus 3 times -2, so -2 plus -6, which is -8. I could try 0. If t is 0, my x coordinate is 0 plus 0, so that's 0. And my y coordinate is -2 plus 3 times 0, so -2. For a third point, let's do t equals 1. T equals 1, we get 0 plus 1 times 1, so that's 1. And we get -2 plus 3 times 1. -2 plus 3 is 1. So take a moment and graph those points on a coordinate axis, and then come back and check your work. So your points should look something like what I have here, with -2, -8, 0, -2, and 1, 2, 1, 1. Which is the line we would have graphed if we had just graphed y equals 3x minus 2. So now what we want to do is take a look at the connection between symmetric form and parametric form. So if I were to take each of the equations for my parametric form of the line, and I were to solve for t, I would get, let's see, x minus x naught over change in x. Again, I'm taking each one of those and I'm solving for t. And then if I were to do the same thing for the y equation, I would get y minus y naught over change in y. Now recall, when we found these points on the line, we used the same t value to find both the x and the y coordinate. So when I am looking at this symmetric form, it is implied that when we solve for t, we are talking about the same t value, so that we can find x and y coordinates that are connected, that are an ordered pair. So over here in my symmetric form, then, I would have t equals x minus x naught over change in x. T also equals y minus y naught over change in y. Now, we're talking about working in space, so now we have a third coordinate. We have a z coordinate, and it really is rather intuitive how we include that z coordinate. It is simply in parametric form. My z coordinate is my known z value plus change in z times time, or t. And if I solve for t like I did with x and y, I get something similar, z minus z naught over change in z. Which means over here, in symmetric form, t is also equal to z minus z naught over change in z.